All right, hey guys. So now that we have an idea of what it means to graph a function, or what it means to graph an equation, that is, graph the infinitely many input-output pairs for a given function, or to graph the infinitely many ordered pair solutions to an equation, let's take a deeper look into a specific type of equation, namely linear equations. So the question here is, how might we graph y equals 3 plus 2x, or equivalently, you could call this f of x equals 3 plus 2x. I just want to make sure we're very comfortable handling something given in function notation. If you see something like f of x equals 3 plus 2x, you can also just consider it something like y equals 3 plus 2x. Now, we've seen a whole bunch of equations just like this before, and we've often seen them in the context of modeling. So something I really like to do when I see an equation like this, and note that this right now has no real-world connections. It's just an equation with two variables, or a function with an input and output variable. What I like to do is begin by kind of associating a story with this one. So perhaps let's use a taxicab example. And let's say that this equation models a taxicab ride. I might say that, for instance, x could be the number of miles you drive, and y could be the cost. So maybe I'll say that the situation is the cost of the taxi starts at $3, right, when you haven't driven any miles, and the cost increases by $2 for every mile we drive. And let's actually take a moment to write that down. All right, and when I go ahead and I put a story to an equation, it helps me find ordered pairs much more easily, and it helps me graph the situation much more easily. So for instance, let's take a look at our table here on the left. I think when you've driven 0 miles, when you first get in the taxi, it costs $3. So put that in here. And we know that for every mile you drive, the cost of the taxi is going to go up by $2. So I know it's going to go up by $2 to 5, then by $2 to 7, then by $2 to 9. So here we've got 4 ordered pairs that we can go ahead and graph right away. So let's take a look at our axes. Let's go ahead and label them X and Y. We know that right when you get in the taxi, it's going to cost $3 when you haven't driven any miles. Hey, look, there's our Y intercept, boom, right there. And every time we go 1 mile, the cost goes up by $2, right? So if we go 1 mile, the cost goes up by $2. 1 mile, the cost goes up by $2. 1 mile, the cost goes up by $2, and vice versa. If you went 1 fewer mile, well, the cost would go down by $2. And those are right there on our table of values as well. Now, if we were graphing an actual modeling situation with a taxi, I don't think we'd put any negative values for X or negative values for Y, right? That wouldn't make sense if this was a modeling problem. But this isn't a modeling problem. This is just kind of an abstract equation or function, and we know that it has infinitely many ordered pair solutions or input-output pairs. And we want to capture them all in a graph. And that includes any negative values of X and or Y that make the equation true. So going back to our table of values, now that we see this pattern, I think it's pretty easy to extrapolate backwards. I think as we go, I don't know if you call this up this table, or as our X values go down, our Y values are now going to go down by 2 each time. So I think it's going to go down to 1, and -1, and -3. Now let's go ahead and put that on our graph. So down to 1, -1, -3. And you can see that these are all creating a line. And right now we're actually exploring equations and functions whose graphs are always going to be lines. So I think we got a lot of information here, and I think we are in a position to go ahead and extrapolate and draw the rest of our line. All right, phenomenal. So what we have here is a graphical representation of all of the infinitely many ordered pairs that make this equation true, or all of the infinitely many input-output pairs for this function. Now note that what I did to make this a lot easier for myself is I went ahead and I put a story on this equation, and that really helped me find ordered pairs in our table of values, and it really helped me to graph. Now the story I came up with had to do with a taxi ride. You can make up whatever story you want. And eventually we're going to become so fluent with this that instead of talking about a taxi ride and the number of miles we drive, you could just equivalently make a story that says, well, y starts at 3. Starting at 3 means when x is 0. And y increases by 2 every time x increases by 1. Just like the cost of the taxi increased by $2 every time the number of miles traveled increased by 1. So I'm actually going to go ahead and write this story involving just y and x now right here. So eventually I'd like us to get to the point where when we see an equation like this in this particular form, we can go ahead and either make up a story that has to do with some real-world situation, or make up a story about y and x that allows us to very quickly make a table of values, and more importantly, very quickly make a graph to capture all of those ordered pair solutions or input-output pairs. Now let's go ahead and let's find the intercepts for this graph. I think the y-intercept is pretty easy. It's right there, right? This was the kind of starting point for either the taxi ride or for y. That is our y-intercept. In this case, the point 0, 3. And note to self, anytime you ever have an equation in this form, y equals some number plus something times x, right here, that's going to be your y-intercept, which is really nice. Now note to self, if you ask me what the slope of this line was, remember that we've talked about slope being a ratio of the change in y to the change in x, right? How quickly is y changing with regard to x? We'll note that for every positive 1 increase in x, there is a positive 2 increase in y. So I think the slope in this case for this particular linear equation is 2. And note to self, heck, there's that 2 right there. This 2, as we've talked about before in our modeling problems, tells you how quickly this variable changes for a 1-unit change in this variable. So that's our slope. And I want to make a point that this form of a linear equation, y equals something plus something times x, it's actually called the slope-intercept form. Why? Because your y-intercept is pretty apparent and your slope is pretty apparent. Let's take a moment anyway to find the x-intercept. Might as well, just for good measure. We'll do this in red. So our x-intercept, we can see it's not a perfect integer. It's somewhere between -1 and -2. Maybe it's -1.5. I don't know. Remember, the way to do that is we're going to take our original equation right here, y equals 3 plus 2x. Excuse me, y equals 3 plus 2x. And if we want to find our x-intercept, remember, the y-coordinate there is always going to be 0 at our x-intercept. So right here, this is the point something comma 0. So if we just substitute in 0 for y, then we can solve for x. So we're going to substitute in 0 for y equals 3 plus 2x. And now it's just a quick equation to solve. I think we're going to subtract 3 from both sides. -3 equals 2 times x. Divide both sides of the equation by 2, and we end up with -3/2, also known as -1.5. That is the value of our x-coordinate right here. So I would say our x-intercept is either -3/2, or you can say the point -3/2 comma 0. So the general idea here that I want us to take away is when you are given an equation in this form, quickly make up a story to describe it. Use that story to make a table of values and create some ordered pairs. And once you've got those ordered pairs, you can go ahead and extrapolate in both directions, graph your line, find your intercepts, and you're good to go. Scrolling on down, let's graph y equals -5 minus 2/3 times x. So this is going to be a little bit tougher. I think the real tough part of this is that we've got a fraction going on in our equation. But once again, let's take a moment to see if we can create a story to describe this situation. I think especially when it comes to negative values, if I want the story to make any sense, I sometimes use temperature because it's possible to have negative temperatures. So take a moment, why don't you pause the video and see if you can come up with a story that describes this situation right here using temperatures and perhaps hours. So a story that I think might make sense is if we're going to call x maybe just the number of hours since the beginning or some number of hours since like 9 a.m. or something, we could say y, or rather, the temperature starts at -5 degrees, and every time an hour goes by, every time the number of hours increases by 1, the temperature goes down 2/3 of a degree. Now that's cool, but I think another way to think of it, which is even more powerful, is to say the temperature started at -5 degrees, and it goes down by 2 degrees every 3 hours. So it's really important that we can do it both ways, but that going down by 2 degrees every 3 hours, I think that's going to be far easier for both making a table and for graphing. All right, phenomenal. So now we have a story that goes along with our equation. The temperature started at -5 degrees, and it decreased by 2 degrees every 3 hours. Now I think this is going to make it really easy to create a table of values. We said that the temperature started at -5 degrees, and every 3 hours that went by, it went down by 2 degrees. So I think it go down to -7, and then 3 hours later, 1, 2, 3 hours later, it went down by another 2 degrees to -9. I'm gonna go, and we can graph these 3 for now. So here we go. Our first point is 0, -5. Let's label our axes. 0, -5. Oh, hot damn, check it out. There's our y-intercept again. That's amazing. And just like we mentioned before, in this particular form of a linear equation, the slope-intercept form, boom, there's our y-intercept. Amazing. And now we have the other 2 points, 3, -7, 3, -7. So that's where we'll go for that one. Awesome. And then we had the point 6, -9, 6, -9. Amazing. I'm sure we could extrapolate from here. We know we're dealing with a linear equation, so it's going to have a linear graph. But we can go ahead and extrapolate here as well. If we go back 3 hours, we should have the temperature go up to -3 degrees, back 3 more hours, up to -1 degree. Let's go ahead and put that on our graph. So, awesome. And now I think we're definitely ready to go ahead and graph this line. Amazing, amazing, amazing. And so here we have the graph of all the infinitely many ordered pair solutions to this equation. Now note to self, I have a whole bunch of different x values on this table of values. I think it's really easy to use all those x values that are multiples of 3, because remember in our story we said the temperature decreased by 2 degrees. every 3 hours. I mean, so might as well just talk about every 3 hours. Note that the other way you could interpret this slope right here, the slope of negative 2/3, is that for every 1 hour, the temperature went down by 2/3 of a degree. And I want to show you that those two interpretations are exactly the same. So for instance, we have our starting point, negative 5 degrees, and after 1 hour, it goes down by 2/3 of a degree, so negative 5 and 2/3. I rarely use mixed numbers, but it's actually going to be helpful here. After another hour, it's going to go down another 2/3 of a degree, so negative 6 and 1/3. And after another hour, it goes down by 2/3 of a degree. Holy cow, we get negative 7 degrees. And I mean, you could continue this trend. Right? It goes down to negative 7 and 2/3, 2/3 of a degree more, negative 8 and 1/3, 2/3 of a degree more, down to negative 9. So I just want to show you that those two interpretations of this slope, negative 2/3, are exactly the same. But the kind of modeling and using it by, it decreased by 2 degrees every 3 hours, I think it's a lot easier for your table of values and for your graph. We've got our y-intercept. We know that our slope in this case is negative 2/3, and it's important to note that our slope is negative, right? Hence, as we read this graph from left to right, our line slopes downwards. And let's go ahead and find our x-intercept. We'll do that in red again. So it looks like our x-intercept is right here. Looks like it's almost negative 8. I'm not sure though, so let's go ahead and confirm. So we've got our original equation, y equals negative 5 minus, 2/3 times x. We are looking for our x-intercept, so we're going to set y equal to 0. So I'm going to go ahead, just for the reader's sake, make it pretty clear what's going on. We're finding the x-intercept, setting y equal to 0. 0 equals negative 5 minus 2/3 times x. Let's go ahead and add 5 to both sides of the equation. 5 equals negative 2/3 times x. Let's multiply both sides of the equation by negative 3/2, the reciprocal of negative 2/3. All right, we end up with, on the right-hand side, these two guys multiply to 1. That's awesome, so we get x. The left-hand side, we get negative 15 over 2. Negative 15 over 2 is negative 7.5. I'm not going to write that mixed number, but it's important that we know that that's negative 7.5. Does that make sense, considering our graph? Yeah, you know what? Maybe I graphed this a little less accurately than I could have, but you could have me believe that this is around negative 7.5. So we're going to say our x-intercept is negative 15/2 or negative 7.5, comma, 0. Awesome. So once again, just showing the power of creating a story to go with an equation, which will help us create a table of values and our graph. So here we've got the equation 4y plus 5x equals 12. Now note, this is not in that very nice form before, right? The two examples we looked at so far were y equals 3 plus 2 times x. Very easy to make a story, very easy to make the ordered pairs and the graph with our y-intercept and our slope. We also had y equals negative 5 minus 2/3 times x. Easy to make a story, table of values, y-intercept, slope, everything's groovy. And remember, this form of the linear equation right here, it's called slope-intercept form. Very important, slope-intercept form. This is not slope-intercept form. Womp womp. In fact, it's actually, this form has a name when it's, something x plus something y equals 12. This is actually called, something x plus something y equals a number. This is actually called the standard form of a linear equation. So for what it's worth, that's called standard form. Okay, so what we're going to do now is, I think what we really want to do is let's transform this into y equals, and in particular, a slope-intercept form. So we're going to want to just solve for y. So let's go ahead and subtract 5x from both sides. 4 times y equals 12 minus 5 times x. Let's divide both sides of this equation by 4. Y equals 3 minus 5/4 times x. Awesome. So now we have a nice slope-intercept form of the linear equation. And I'm actually going to walk through this, but why don't you, for practice, pause the video, see if you can come up with a story for this. Let's use hours and temperature again. See if you can create a table of values, see if you can create the graph, see if you can find the x-intercept, try all those things. And if you have trouble, or when you're done to check your work, play the video and we'll see how it went. All right, so if I were to make a story to go with this equation involving temperature and hours, I might say that the temperature started at 3 degrees right at the beginning, and the temperature decreased by 5 degrees every 4 hours. You could also say that it decreased by 5/4 of a degree or 1 1/4 of a degree every 1 hour, but I think it's more helpful to say the temperature started at 3 degrees and it decreased at a rate of 5 degrees every 4 hours. Phenomenal. Let's use that to our advantage. Let's create a table of values. I haven't filled in any x values because it's kind of up to you to decide. I think it's going to be best to use x values that are multiples of 4 because we're talking about a temperature that's changing by some amount every 4 hours. So we'll start at 0. I like to center my x values right at 0. Right, so at the beginning, the temperature started at 3 degrees. There's going to be our y-intercept again, just like we thought. And 4 hours later, the temperature will go down by 5 degrees. So down to -2. 4 hours later, down by 5 degrees. we can extrapolate back up now. 4 hours earlier, the temperature would have been 5 degrees greater. 4 hours earlier, the temperature would have been 5 degrees bigger. So you can see that, okay, maybe this isn't going to fit on our graph, but good to know anyway. So let's go ahead and graph these ordered pairs. Here, let's label our axes. So we've got the ordered pair 0, 3. Again, our y-intercept, ding, ding, ding. That's awesome. Y-intercept is 0, 3. Let's make a note of that right here. So our y-intercept. All right, so we know that for every 4 hours that go by, the temperature decreases by 5 degrees. I mean, we've got our table of values already, but I know that if the hours go by 1, 2, 3, 4 hours, the temperature will go down 1, 2, 3, 4, 5 degrees. It's going to be a very cold day. A very cold day indeed. Another 1, 2, 3, 4 hours. Another 1, 2, 3, 4, 5 degrees. Down to -7 degrees. Woo, freezing. And of course, we can extrapolate in the other direction. If we had gone back in time 1, 2, 3, 4 hours, we expect that it would be 1, 2, 3, 4, 5 degrees warmer at that time. And I think at this point we have all of the ordered pairs that are really going to fit in our graph. So let's go ahead and let's draw that line. And note to self, check it out. While I was graphing this point over here, I think I kind of miscounted a little bit or something. And one more reason it's great to draw a whole bunch of points and extrapolate because, hey, if you make a mistake, you might be able to notice it. And look, I graphed the y value at -5 instead of -7. Oops, pardon me, and whoop, fixed. Awesome. I'm going to draw my arrows. And now we've got a graph of all of the ordered pair solutions to this equation. We already have our y-intercept. We definitely know that our slope in this case was -5/4. I'm just going to write that in. Right, that was the ratio of the change of y values to x values. Last thing to do is let's find the x-intercept. So our x-intercept, it appears something a little bit more than 2, maybe 2.5, I don't know. Let's use our equation to find it out. So here's our equation, y equals 3 minus 5/4 times x. We are going to try to find our x-intercept. So we're going to set y equal to 0 and see what happens. All right, so 0 equals 3 minus 5/4 times x. Subtract 3 from both sides. -3 equals -5/4 times x. Let's multiply both sides of this equation by -4/5. All right. Note to self, these two guys right here are going to multiply to 1. So on the right-hand side of the equation, we just have x. On the left-hand side, we have +12/5, which is about 2 2/5. Does that make sense, kind of looking over here? Yeah, buddy, it certainly does. That, if you told me that was 2 2/5, I'd believe it. So our x-intercept in this case will be 12/5, 0. Now, I do want to make a comment here, really important. I mean, it's not like this was a particularly difficult equation to solve, but there were fractions and stuff. It was kind of a pain. Maybe we could have made a mistake. Note to self, the standard form of a linear equation right here is not good for a lot of things. Doesn't have the slope, doesn't have any intercepts kind of readily available. But you know what it really is good for? It's actually good for finding intercepts. Because imagine I found the x-intercept using this equation instead, 4y plus 5x equals 12. And we know that to find the x-intercept, you set y equal to 0. And if we set y equal to 0, well, 4 times y is 0. You just end up with 5x equals 12. Holy cow, not so bad. I think we know how to solve that. Divide by 5, x equals 12/5. So just want to put it on your radar that while the standard form of a linear equation isn't good for much, it can be pretty helpful for finding intercepts. All right, so general takeaways from this is if you've got a linear equation, I like to put it in slope-intercept form. Maybe create a story that corresponds with it to help me find some ordered pairs on a table, graph them, extrapolate, and find the intercepts. And standard form of a linear equation isn't great for much, but might be good for the intercepts. Okay, hope you found this helpful, and I hope you enjoyed.